Good morning. Today's topic is Introduction to Spectroscopy. Spectroscopy is a general term referring to the study of interactions of various types of electromagnetic radiation with matter. Exactly how the radiation interacts with matter is directly dependent on the energy of the radiation. Spectroscopy, so coming to the definition, spectroscopy is the study of the absorption and emission of light and other radiations by matter. This involves the splitting of light. When light enters into the matter, it splits into different wavelengths. So, more precisely, the electromagnetic radiation, when enters into the matter, it splits into constituent wavelengths, which is done in much same way as the prism splits light into a rainbow of colors. So, spectroscopy is used as a tool for studying the structures of atoms and molecules. Large number of wavelengths emitted by these systems make it possible to investigate their structures in detail, including electron configurations of ground state and various excited states. Coming to the history of spectroscopy, began with Isaac Newton's experiments on optics. Newton applied the word spectrum. Newton is the man who coined the term spectrum to describe the rainbow of colors that combine to form white light and that are revealed when the white light is passed through a prism. During the early 18th century, Joseph von Fraunhofer conducted experiments with the dispersive spectrometers that enabled spectroscopy to become a more precise and quantitative scientific technique. So, he is considered as the father of spectroscopy, modern spectroscopy. Now, coming to the interaction of radiation and matter. If matter is exposed to electromagnetic radiation, for example, infrared light, the radiation can be absorbed or transmitted or reflected or scattered or undergo photoluminescence. What is photoluminescence? It is the term used to designate a number of effects that are fluorescence, phosphorescence and Raman scattering. Effect of radiations on matter. What are the effects when radiation interacts with the matter? If high energy ultraviolet and visible wavelengths affect the energy levels of outer electrons. When infrared radiation interacts with the matter, it is absorbed by matter, resulting in rotation or vibration of molecules. Radio waves are used to nuclear magnetic resonance and that affect the spin of nuclei in the magnetic field. Coming to the classification of spectroscopy. One way of classifying spectroscopy is the nature of interaction between the energy and the material. These interactions include absorption, emission, resonance frequency, elastic and inelastic scattering of radiations. Another way of classifying spectroscopy is based on the type including the matter, depends upon the type of matter, that is atoms, molecules, nuclei and crystals. Coming to the continuing the classification of spectroscopy. Spectroscopy is classified into these types. One is atomic spectroscopy, that used to quantify the sample's composition. The next is ultraviolet and visible spectroscopy, that measure the concentration of samples using the principles of Beer-Lambert's law. Infrared spectroscopy is used to determine the functional groups present in a sample. Then, coming to the Raman spectroscopy, it provides a molecular fingerprint of the chemical composition and structures of samples. Nuclear magnetic resonance is used to identify the structure of a compound based on the spinning of nuclei. There are three types of atomic spectroscopy. They are atomic absorption spectroscopy, atomic emission spectroscopy, and atomic fluorescence spectroscopy. What is atomic absorption spectroscopy? It absorbs ultraviolet or visible light to transition to higher energy levels. When matter absorbs ultraviolet or visible light, its outer electrons will elevated from the ground state to the higher energy levels. Atomic absorption spectroscopy quantifies the amount of absorption of ground state atoms in the gaseous state. So, it is commonly used in the detection of metals. The second one is atomic emission spectroscopy. In atomic emission spectroscopy, atoms are excited from the heat of a flame or plasma or arc or spark to emit light. This is used the intensity of light emitted to determine the quantity of an element in the sample. So, quantity of light emitted is quantified or it is measured to calculate the quantity of element present in the sample. Third one is atomic fluorescence spectroscopy. It is a beam of light that excites the analytes present in the sample, causing them to emit light. Fluorescence from the sample is then analyzed using a fluorometer, and it is commonly used to analyze common organic compounds. Let us have a look at the electromagnetic spectrum. First comes gamma rays, then next X-rays, UV rays, visible light, IR, infrared, microwave, and then radio wave. This is the common electromagnetic spectrum we use for various applications. Here, the wavelength is given in meters, centimeter, and nanometer. Below that is the frequency, and this is energy of each radiations. When we examine the wavelength and energy, as the wavelength increases, energy of the radiation decreases. That is the relationship between wavelength and energy of electromagnetic radiations. This is the table which shows the type of radiation, frequency range, wavelength range, and type of transition. We have gamma ray, X-ray, ultraviolet ray, visible ray, near infrared, microwave, and radio wave. Its frequency is given, its wavelength is given, and type of transition it happens in the material. When light interacts with matter or light absorbed by matter, a portion of light is absorbed and another portion is transmitted. That means a particular wavelength is absorbed and a complement color is transmitted. The color of an object we see is due to the wavelength transmitted or reflected. Other wavelengths, all other wavelengths are absorbed. So, more the light absorbed, darker will be the color. So, in spectrochemical methods, we measure the absorbed radiation. This chart shows the wavelength, its absorbed color, and its complement color. So, a particular light is absorbed and its complement color is transmitted. This chart, this diagram shows the color and its complement color. That means, if yellow color is absorbed, its complement color, that is violet, is transmitted. If blue color is absorbed, its complement color, orange, is transmitted. This table shows the absorbed color and transmitted color, or the complement color. Coming to the radiations, its properties. Distance of one cycle or one wave is the wavelength, that is designated by the symbol lambda. The frequency is designated by nu, is the number of cycles passing a fixed point per unit time. So, lambda is equal to c by nu, that is c is the velocity of light divided by the frequency. So, shorter wavelength has higher energy. According to this equation, E is equal to h nu. This is why UV radiation from sun burns you, and visible light has no burns. Visible light does not produce any burns to us. So this equation says that energy of a particle of light, E, called a photon, is proportional to its frequency, nu, by a constant factor h. H is called Planck's constant. We see only a very small portion of the electromagnetic spectrum. That is, we can see only this region, visible region. All other regions we cannot see with naked eye. So the wavelength range of UV is from 200 to 380. Visible range is from 280 to 780. And infrared range is from 0.78 micrometer to 300 micrometer. That is the wavelength range of all these three radiations. Among these three, only this one is visible to the naked eye. Now, coming to the particle nature of radiation, electromagnetic radiation is described as having the properties of particles. Molecules exist in a certain number of possible states corresponding to the definite amount of energy. So, molecules can absorb energy and change to higher energy level called excited state. The amount of energy absorbed in this transition is exactly equal to the energy difference between the states. So, when atoms exist in different energy levels, the quantity of atom absorbs depends upon the energy level of the atom. This is an example of energy level diagram of sodium. Here, this is the ground state energy level, this is the elevated state, and this is the next energy level. So, when sodium absorbs some amount of energy, first it is elevated to the E1 level, and if it absorbs more energy, it will be elevated to the next energy level. When it loses energy, it will return to the ground state. This is in the case of sodium atom. Here, this diagram is the energy level diagram of a simple molecule. Molecule means it contains more than one atoms. So, different atoms will absorb energy at different quantities. Excitation to the next electronic level is caused by absorption of specific wavelengths. So, each molecule can absorb a specific wavelength of light, and it will receive some amount of energy from that absorbed radiation, and depending upon the quantity of radiation it is absorbed, it is elevated to the next energy levels. When it loses the absorbed energy, it will return to the lower energy levels, and it need not be necessary that it will reach at the ground state. After attaining this level, when it loses some amount of energy, that is called a relaxation, it can return to the E1 energy level, or in the E4, E2, E4, E3, E2, E1. All these vibrational energy levels are just above the ground state. So, when a molecule returns by losing some amount of energy, it need not be, it is not necessary to reach at E0 state. It can reach somewhere here in the vibrational energy levels. Coming to the types of optical instruments, spectroscope means it is an instrument that shows the spectrum, and the detector is human eye. With the naked eye, we can observe the spectrum through a spectroscope. Spectrograph means it is the photographic emulsion or photographic film is used as the detector. So, we will get an image in the photographic film. Spectrometer, it has an photoelectric readout. Monochromator is the part of spectroscope that allows only one wavelength or only a single wavelength of light, or it has one exit slit. A polychromator means it has multiple exit slits. Spectrophotometer, it is the electronics takes ratio of two beams, percentage transmittance, may be at same or different wavelengths, may be single beam or double beam. That is a spectrophotometer. Coming to atomic electron transition. Atomic electron transition is a change of an electron from one quantum state to another within an atom. So this happens within an atom. It appears discontinuous as the electron jumps from one energy level to another in a few nanoseconds or less. So it is also known as atomic transition or quantum jump or quantum leap. Electron transitions cause the emission or absorption of electromagnetic radiation in the form of quantized units called photons. The electron jumps the shorter wavelength of photon emitted, meaning they emit different colors based on how far they jump. Next is molecular electronic transition. In molecular electronic transition, it takes place when electrons in a molecule are excited from one energy level to higher energy level. The energy change associated with this transition provides information on the structure of a molecule and determines many molecular properties such as color. This diagram shows the difference between atomic electronic transition and molecular electronic transition. In atomic electronic transition, atoms are excited from ground state to higher energy levels, that is E1 or E2. When they lose energy, they will return to the ground state. But in the case of molecular transition, when it receives energy, it will be elevated to the higher energy levels, and when it loses the energy, it will return to the vibrational energy levels and not to the ground state. That is the difference between atomic energy transition and molecular energy transition. Coming to the applications of spectroscopy, it used to determine the atomic structure of a sample, studying spectral emission lines of the sun and distant galaxies. It is very widely used in space exploration, QR monitoring of composites using optical fibers, estimating withered wood exposure times using near-infrared spectroscopy, measurement of different compounds in food samples by absorption spectroscopy both in visible and infrared spectrum, measurement of toxic compounds in blood samples as well as food samples, non-destructive elemental analysis by X-ray fluorescence, electronic structure research with various spectroscopes, redshift to determine the speed and velocity of a distant object, determining the metabolic structure of a muscle, monitoring dissolved oxygen content in freshwater as well as marine ecosystems, altering the structure of drugs to improve the effectiveness of drugs, characterization of proteins, respiratory gas analysis in hospitals, finding the physical properties of a distant star or nearby exoplanet using a relativistic Doppler effect, in ovosexing to determine the sex of eggs. So these are the important applications of spectroscopy. Coming to the summary, if matter is exposed to electromagnetic radiation, for example infrared light or visible light or UV light, the radiation can be absorbed, transmitted, reflected, scattered, or they may undergo photoluminescence. And photoluminescence is a number of effects including fluorescence, phosphorescence and Raman scattering. So spectroscopy is the study of interactions of various types of electromagnetic radiation with matter. Thank you.